start with this perspective, and one reason is that it can be easy to assume when you hear about some new and interesting technology that it's going to take a foothold immediately and create a profound change in the world immediately. But that's not what happens in energy. It takes a while. It takes technology, regulation, and business model to come into sync for these markets to move. Let's just walk back a little bit and let's get a sense of what we're looking at here. So first of all, you can see on the y-axis, TWH, that stands for terawatt hours. Just think about it as amount of energy being created. And then you can see with the different colors what kind of primary fuel is providing that amount of energy. And you can see all the way from traditional biomass all the way up to modern things. But let's look all the way back. So prior to 1850, traditional biomass was what created our energy. And what did you use that energy for, right? You used that energy to cook food, to keep you warm, and to light your homes, right? And that energy was decent at doing that. It would have been smoky and sooty inside your house and other things, but it provided that very at least basic and fundamental needs associated with energy. Simply having that energy makes a profound difference on someone's lives versus not having energy source at all. So traditional biomass, when we say that, what is that? That's people burning wood. It can be, burning animal refuse or peat or things like this that are just laying on the ground. But in 1859, oil was struck in Titusville, Pennsylvania, and we began the story of oil that has really been transformational throughout our world. And I think one thing that's kind of interesting is if you take a look at, it took really, you're looking at 65 years before oil began to displace coal in any way, right? So at first, traditional biomass, then coal starts picking it up. You're digging a little deeper and getting coal. But it took a profound long period of time for oil to really start picking up any share of our energy at all. And why was that? What happened in 1925? You completed a pipeline. If you didn't have a pipeline, you had to get the oil out of the ground, store it somewhere, truck it somewhere else. There weren't Class 8 trucks back in the year 1900. It was difficult to get things from here to there. The next evolution would have been via trains. Difficult to get the oil where it needed to be. So you can see it had very little impact. But after 1925, when you brought together the energy source and its transmission source, that's when it really began. I'm mentioning this now because there are some parallels. I want you to think about it. Just because you see a lot of windmills or solar panels somewhere doesn't mean that it's providing a large amount of the energy we use. What's one reason why? Well, we don't have those pipelines. It turns out in electricity, we call those transmission lines. We don't have enough of those to get it from where it's made to where it's used. So think about that long period of time, 60 odd years pass before oil even makes a dent after it's stretched. What's the next thing to happen? Well, natural gas pipeline from Gulf Coast, Pennsylvania to New York completed. And this, once again, is when we finally start to see the purple color, which is natural gas, begin to take off. Prior to that, very small. 1954, the first nuclear reactor was connected to the grid. Wasn't in the U.S. like a lot of people think. It was in the Soviet Union and actually in Russia at the time. And we begin the modern era of nuclear power. In 1980, the first utility scale wind farms are installed in California. And just a year later, the first megawatt scale solar plant goes online in California. So as we look at these dates, and as we think about this arch, you may think that, and we see solar, we see wind all the time. We're going to talk about microgrids tonight. You're going to talk, I every day, hear stories about hydrogen and carbon capture and all these other interesting things. We want you to realize it takes some time. Even now, look at what color on this graph: solar, wind, and let's look at those two, solar and wind. They're so small, you can barely even see them on this graph. Even now, all those years later, in terms of the amount of energy they actually provide. So let's just dig into that on the next slide. What you're looking at here is what percentage of each of those energy sources, and this is a graph where it's 100% energy on the left, and on the right is the terawatt hours needed. So the idea being, this essentially says, okay, this is what you might, if you ever done a PowerPoint presentation, this is a stacked graph. So, you know, what percent kind of is everything and how much energy is it? The reason I want to show you this is because this graph goes out beyond what we just looked at. What we just looked at ended in 2021. This takes us to 2040. And let's take a look at some of these. So if we look at that biomass and you know, animal stuff, you know, you can see that that's fading out, you know, almost to zero over that time period. But coal still stands pretty strong for another decade or so. Oil shrinks but maintains pretty strong. Natural gas remains strong and maybe even increasing percentage as we think about transitioning away to other things. Hydro remains fairly flat. That's because there's only so many places that you can put big hydro, and they're very capital expensive. But you do start to finally see quite a bit of solar growth, wind growth over the next 20 years. So it's coming, but it's going to take a little bit to go get there. Let's talk about what these things are happening. So if you think about those two graphs we just looked at, this was the story of the natural gas, oil, and coal, really all the way up to the 1970s, 80s, and 90s, even providing the preponderance of our energy. And of course, in the 1950s, you know, we began to introduce these new energy sources, nuclear, wind, and solar. But there's a problem, right? And the problem is that with those fossil fuels on the left, it wouldn't be pretty, it wouldn't always smell good, but you can cook your food, you can light your house, and you can get warm next to all three of those things. I wouldn't recommend, you know, cooking, lighting, or eating next to a nuclear reactor, even though I did live on a sub for 4 years. Of course, windmills can't put a pancake very well on them. They're not great at that. And you know, solar panels don't really put off a lot of light where you need it, at least. And so they create electricity, but they don't directly substitute for those fossil fuels on their own. Something else has to occur. And what has to happen? It's electricity. So when you hear people talking about electrification, electrify buildings, right? Electrify your home. The reason that's so important is you can't substitute those things on the left with the things on the right until you electrify. It's not easy to do that at all. It's going to take some enablers, though, because having solar and having wind, they do provide nearly carbon-free or carbon-free sources of electricity, but they're intermittent in nature. You can't necessarily count on them to be there when you need it. So some strategic enablers that have to occur over this next few decades in order for those things on the right to really substitute those things on the left is some sort of battery energy storage or energy storage in general. Hydrogen is a key enabler as well. We'll be going to that a little more today. And carbon capture. So while I am phasing out those things on the left, how can I reach my sustainability goals? So carbon capture, hydrogen, and energy storage are three enablers that's going to allow those disruptors on the right to eliminate as much stuff on the left as we can. So today's story will be a little bit that in the middle, that electricity piece. That's where the microgrid world lives. How does that work, and what are we looking at? So what is a microgrid? Well, you can go ask the U.S. Department of Energy the following definition: an integrated energy system consisting of interconnected loads and distributed energy resources, which can be controlled as a single entity and operate in parallel with the grid or in an intentional islanded mode. So what do those things mean? So first of all, you've got loads, right? So these are things, what do each of these words mean? These are the things that use power. It's your lights, it's your stove, maybe if it's electric, it's your electric car, maybe perhaps today. What are distributed energy resources? There's three parts to this one. Distributed energy resources produce electricity, so that might be solar, wind, or a diesel generator. Storage is a distributed energy resources, and something called flexible loads. So some loads, it's hard to turn them off when you need to. You can buy, as you're probably aware, smart light bulbs these days, or EV chargers with automation inside them, or hot tub controllers that can choose to come on and off at certain times. Once you add that intelligence to load, you've taken it from a passive load to a distributed energy resource. And all this simply means is that I'm applying digital things over top these aspects of the electrical grid: production, storage, and loads. And if I can digitalize those things, I can create situational awareness. Situational awareness is understanding what variables are correlated to the energy I'm using now and how I'm interacting with the grid to get the outcomes that I want. Now, we might not all want the same outcomes. We're going to talk about what those are and what some of the differences are here in just a slide or two. A microgrid controller, its story and its purpose is really to orchestrate this process. We go from situational awareness to automation to drive outcomes. We'll talk about what some of those outcomes that you might want, but you can imagine there might be, I'd like lower cost. I'd like to be greener. I'd like to have my lights come on when the power grid goes out. Those are some of the things that a microgrid controller can solve for. But its real key job is to connect to each of these things, to understand what they're doing now, to predict what they're going to do in the future, and put this grid in a condition such that it is achieving optimal outcomes. The microgrid controller then interfaces with the grid. And in doing so, it's going to allow this campus, this integrated energy system, as it's called, that's all we're really talking, that's everything inside the microgrid controller, to connect and interface with the grid. For the past 100 years, that wasn't a two-directional arrow between the grid and a building. It was one-directional. The utility forecasted how much energy they need to make, they made it, and they drop it off at your home or your apartment building or the factory that you work at. And the consumer had no real role in what that grid interface looked like. They weren't really incentivized in any way to do something different. They simply got a bill once a month and had to pay it, whether it was as green as they liked it or as reliable as they wanted, or it cost what they wanted, didn't matter. You got to go and pay it. In this new world of a microgrid, we take that one-way arrow and we make a two-way arrow. I can choose to make electricity locally that is more attuned to my business needs. And in some areas of the country, I can even sell that back to the grid and share that benefit with other people that might like energy the way I like it. We're going to talk about that here in just a little bit. So what are those things that people are looking for? What are those better energy outcomes? Access to energy. Of course, there's large parts of the world in which there is no electrical grid, and people do not have access to energy today. By the way, over 1 billion people are without access to any electricity, and 1.6 billion people at least have access to only intermittent energy. When you live in a world in which you do not have access to energy, you are still burning that, biomass in your home. You don't have the light for children to be able to study, to achieve the best things they can. Over 4 million people die a year due to indoor air quality issues from burning things inside their homes. As you can imagine, this is primarily in Africa, India, and other Southeast Asia areas. Without an automated, things in the home like a washing machine and a stove and a refrigerator, women work much longer hours. They're often taken out of school to do housework, which of course diminishes their prospects down the road. Access to energy is vitally important. Even here in the US, we're finding places now where it takes years to get connected to the grid. There's a concept called time to power. And what that really means is that it is the electric grid is at near max capacity at a lot of spots, and it has to be built out to service new load. And that can take a long time because utilities have to go through regulatory hurdles. So even now, there's places in the US, especially those fast growing areas like maybe Texas, that people don't have access. They might want to build as a residential consumer, you would, but let's imagine you wanted to go put down a 100 megawatt data center. You probably couldn't get that service for 3 to 4 years. So creating that your own access is one reason someone might want it. Lowering costs, of course. Can I make energy for cheaper than I can buy it? Or can I make energy in a way that has more predictable costs? So let's compare something there, right? So solar energy has no marginal fuel cost. What that means is that unlike a natural gas engine, where for every piece of energy I make, I have to pay for gasoline to go in, right? So it's got a marginal fuel cost in that case. Solar energy, we haven't found a way to tax photons coming from the sky yet. So right now, you can create as many kilowatt hours as you want, and you're not paying more per kilowatt hour. Yes, you've got to go put the initial infrastructure in, but you're not paying as you use it. And what that means is that you have a more predictable energy cost. If I were to put a solar plant in for someone, I could guarantee them an energy price for 20 years. You can't do that today with any other fossil fuel because you don't know what the marginal cost is going to be. Resilience, we'll talk about that in a little bit, but the grid is increasingly frail. Even places where I think that no one had imagined the grid would go off before, like rolling blackouts in California and problems in Texas, we see that the grid is having trouble servicing our communities. And so having extra resilience could be important. And finally, sustainability, right? Using energy in such a way that we're not creating more damage to this planet. So let's step back a second. I just said that there was 1 billion people without electricity, another 1.6 billion people that only have intermittent energy. We talked about the amazing things that electrification brings, better outcomes for many people. We've got to find ways to get them on those folks onto electricity. However, the rest of us are using the grid and electricity in such a way that we're causing permanent harm to our planet. So we've got to deal with those two things at once. We've got to bring more people onto the grid, but at the same time, those of us who do have access to it have got to drastically reduce how we're using it and the environmental implications of what we're doing. So this is the fundamental challenge that this industry is facing, bringing everyone on and reducing the energy intensity of everyone else, or doing so in a more sustainable way. Now, you can imagine that people have different outcomes that they might desire. Let's just look at two scenarios. I imagine in your hometown today, you probably have a hospital and you probably have an elementary school, and they may even be on the same feeder from your utility. So let's imagine that feeder goes down. The ramifications of that hospital are pretty profound. A patient could die on the operating table. A surgeon could get sued. The hospital could have all kinds of problems. Resilience means a lot to them, right? Being able to keep that grid on, it means a lot. What about the elementary school? Okay, power goes out. Well, send the kids to recess and the teachers to a smoke break, I guess, right? So you can imagine that they might solve in a different way, right? They might think about, what? Cost means a lot to me. I've always got, tight budgets here at the school. I'm going to solve. When we put in a microgrid and we digitalize those things, we create a story where we can tailor energy to a unique consumer's objectives. And that's this other definition. This isn't the DOE definition of interconnected loads and supply. It's a digitalized and automated energy system that empowers consumers and suppliers to make wise choices at the intersection between energy smartly acquired, locally produced, and efficiently consumed. This is the why behind microgrid. And your why might be different than someone else's why, but a microgrid has to be able to solve for each of those different outcomes. All right, so let's dig into that a little more. We talked about what those important things. We talked about cost. I mentioned lower, more predictable costs. A concept called utility tariff optimization. What that means is that you may be charged, or the place that you work may be charged a different amount for the energy you use based upon time of day. Or you might get what's called a peak demand charge, that whatever the peak amount you use at any given time, you're going to get a penalty associated with that. Another cost savings mechanism is capital expenditure avoidance. And what this means is, let's imagine that the transformer to your business is just about to be overloaded, or your main service panel, And, that's going to be, at an industrial facility, that could be hundreds of thousands of dollars to go replace that. If you were to serve some of your energy locally, instead of requiring all the electricity to travel through that transformer, you could avoid that capital expenses. Incremental value streams from energy markets. What this means is that in some parts of the US, you can monetize electricity that you make. Sometimes you can sell it back to the grid. Other times you can participate in something known as virtual net metering, where I can make electricity at one of my facilities and take advantage at another facility. There are also complex energy markets that utilities use in order to balance the grid. And I'll use a technical word here for a second in case there's any technical folks on the phone, but it's called ancillary services. And essentially, these are the services that keep our grid running. Normally, utilities put infrastructure in that provide these services. There are things like frequency response and voltage response and load following and black start capabilities. These are things that utilities have historically put in to make the grid run like it should. But if end users with microgrids are willing to do this, then many regulators have said, gosh, let's let them do it. They might be able to do it cheaper than a utility. So that's another, cost benefit for a microgrid. Access and resilience. So this is a story of we're getting energy to where there's no bulk power grids. This is also the story about protecting sensitive and critical loads from poor power quality. You've probably seen voltage sags and voltage spikes. You may even had a TV fail. The ramifications are much worse with some industrial processes. Literally millions of dollars can be lost based upon, power quality issues. And finally, sustainability. That might be reducing your carbon footprint. It might be achieving the commitments that you've made to your customers, your shareholders. Increasingly, we've seen it of attracting and retaining talent for your business. People want to work for a place that understands this challenge in front of us and is willing to do the right kind of things around that. And if you do those things, you're going to improve your brand, which matters to all the stakeholders above. So in a sense, what a microgrid does, I use the word, they decommoditize energy. When you buy energy from the utility, you're buying in a unit called a kilowatt hour. And you didn't have much data on that kilowatt hour 5-10 years ago. In this fashion, you are able to prescribe how green, how resilient, and some aspects of the cost associated with it. So microgrids are key to decommoditizing energy and therefore solving for the ends that matter most to you. So types of microgrids, there's 3 types. One is a grid-tied microgrid. This kind of microgrid is generally the simplest microgrid, and that they require the grid to operate. So this might be the story of many residential microgrids. You put solar on your roof. The solar, as long as you're connected to the utility, it's providing loads. You're getting maybe some kind of ROI associated with that. You might even heard a fancy word called VPP, virtual power plant. And what that means is that the utility or an electrical wholesale market is tapping into that grid-tied resource, and they're using it for whatever ends they're solving for. So this is a story of providing services to the consumer, providing services back to the utility. However, it's not really a story of resilience. Islandable means that, yes, I can operate grid-tied, but when something happens, I can separate from that grid and operate as my own oasis. This is probably what people mostly think about when they talk about microgrids, is this islandable microgrid. But by the way, there's a pretty significant cost difference going from grid-tied to something that is able to manage the own power within a grid. So it's not a trivial jump from grid-tied to islandable, but it does provide you power when the grid's out, whereas the grid-tied doesn't. And finally, you get to the most sophisticated, which is an off-grid microgrid. And really the only difference between islandable and off-grid is that when you're going to run something completely off-grid, you can't depend upon the power grid for any services at all. So you've got to buy components that are designed to run all the time. Versus islandable, I might be able to use a standby generator, take it down for maintenance, no big deal, the grid's available. if you're going to go off grid and you take your generation down, everyone on the grid's going down. So you got to think about what you're buying and how you're buying it a little different. But those are the three types of microgrids that you can get in the market today. So let's talk about these things: energy price, and we'll talk about each of those metrics now. We'll talk about price, we'll talk about sustainability, and we'll talk about resilience. So this is a map. This is 2019. I was looking for something newer, but I didn't find a nice clean graph of something newer. By the way, there is something called EIA.gov, Energy Information Agency. It's part of the U.S. Department of Energy, and you actually can get very detailed energy pricing there. And it's got some tools, but it doesn't make a cool map like this. But I do recommend you check that out if you're interested in energy. You can look up easily the generation source of where you live, the carbon footprint of it. You can look up the grid price. You can look up the industrial price, the residential price, the commercial price. You can really understand a lot about the energy use. This is a simplification. This is the average retail prices, and the red is the highest. And so you've got California, and then some of New England. And then as you drop down, you can see that you're picking up, some of them you start to get into the mid-Atlantic. You can tell this is a year or two. You can tell it's 2019 though, because I bet if you looked at your bill right now, you would see it's a lot higher than 10 to 12 cents. In some cases, 30% increases, due to the increased price of natural gas. Remember back to that graph we looked at, second or third slide coming in, how natural gas actually sets the price for energy markets. They say natural gas is on the bubble, and that's just because it ends up servicing most of the load because it's flexible and can be moved up and down. So natural gas ends up setting the price in most markets in the U.S. Finally, the lowest cost states, you can see where some of those are. There's a lot of things that contribute to the price: energy policy, sustainability policy, this access to natural resources, good pipelines, good transmission systems. Those are all things that play into getting those, what's going to set the price. So what's the cost of the grid and its drivers? I kind of tease this out a little bit, but pick the electricity residential price. This is a little bit newer data. So I pulled this off of EIA, which is the U.S. Energy Information Administration. And you can see there's been a pretty profound raise here, as I mentioned. So you get from 2019, and this was the residential race. Now, the last graph you looked at was blended industrial, commercial, residential. Residential rates are generally the highest rates because you're not buying as much bulk. So this is going to be a higher number than you just saw. But you can see this pretty profound price spike going on here in the projections out to 2024. In other words, it's going to get worse before it gets better, if I were to say one thing about this. So what's driving that? And I already gave the answer earlier on, and it's the electrical generation mix. So this is the generation mix for the Mid-Atlantic. So once again, you can get it from that EIA.gov site. You can see where you get your power, where you are getting it. This blue, natural gas. So natural gas is serving your market. You're beginning to get an uptick. That yellow line, that is all renewables together. So that's solar plus wind plus hydro. So you can see that it still, though, is less than 1/4 of the amount of electricity that comes from natural gas today. And of course, coal is something that you've had for quite a while, continuing to drop off over time. So why is your price is what it is in your area? It's going to be the price of natural gas. So if you wonder where you're, and remember, electric utility rates, they're always a little bit behind because they have to get permission generally to embed generation rate hikes into what they're charging you from the public utility commissions. So you're always going to be a little bit delayed for that price to go up, and then you'll be a little bit delayed to get off that high price. Okay. And that factor about natural gas, it's the biggest factor in across the U.S. today. And you'd see other regions look pretty similar to this. So let's talk about different types of generation and its impact upon cost. So there's a concept called the levelized cost of energy. And this is a metric that those of us in the industry use to determine how cost effective any given generation asset is. And it has three main elements to it. C, along top, that's the capital cost. How much does it take to build a plant? And let's just start with that column, the capital cost. Well, the capital cost, and notice it's qualified per megawatt. So this is actually kind of a marginal capital cost here. Coal, for purposes here, I won't go the difference between open cycle and combined cycle, but we don't have time for that today. But you can see these are all relatively low cost per megawatt. Why is that? A, they're very big plants. Each of these plants, these natural gas plants and coal plants, hundreds of megawatts, in some cases approaching a gigawatt. Therefore, you can put a lot of capital because you're dividing it by a lot of power generation. The second thing is, these are very mature technologies. They've been around forever. There's lots of competitors. So you've got a competitive marketplace that's pretty mature and it's big, and you just have the dynamic for low capital cost per megawatt. Now let's go to the yellow ones here, the ones that are a little more per megawatt, but a little less than some of these others. You've got onshore wind, solar, and fuel cells. So these represent technology that they all have some degree of maturity, but they haven't been in the market as long as coal, open cycle, and natural gas. Generally, they're smaller as well. So yes, there are huge wind farms that are hundreds of megawatts, but each of those single onshore wind turbines you see, those are only between 2 and 4 megawatts generally. And solar, for solar, it takes 4 acres of land to have 1 megawatt. So sometimes you'll see a whole field of solar. You might be, oh my gosh, that's enough to power the city. Well, that entire field of solar, I mentioned the size of one large wind turbine was between 2 and 4 megawatts. Well, that means it would take anywhere between 8 acres and 16 acres of land just to make that same amount of electricity with solar. There's another factor in this called capacity factor. I'll get to that later. But so these three, onshore wind, solar, and fuel cell, they represent competitive capital costs per megawatts, but they're still not going to beat, in terms of capital costs, those top ones. And finally, you get offshore wind, hydro, and nuclear. The nuclear challenge, there's a lot of people looking to address that right now with the idea of small modular nuclear reactors. And this is what everyone hopes might be creating identical reactors over and over again. The reason the nuclear reactors, even though they're massive as well, they can be a gigawatt as well, but we don't have the same standardization, and there's much more oversight, and there's much more codes and standards around nuclear. The cost tends to be higher because of that. Hydro, the cost tends to be higher. They're infrastructure heavy for how much energy they use. You can't put them everywhere. And offshore wind, you've got to deal, they can be very large, but you've got to deal with all the challenges associated with building them. Now let's go to the next one, marginal fuel cost. So it's one thing to know how much, just to take this analogy back 1 second, marginal fuel cost, maybe that's, if you were to equate that to a vehicle, it's the cost of the vehicle per person that it seats or something, right? Just think about it in that way. So something might seem like a good deal because it's cheap per person, but if it gets terrible fuel economy, it might end up costing you a lot more. And that's really what this marginal fuel, M stands for marginal cost. That's what marginal fuel cost is. How much is my raw material that I'm putting in it? So let's talk about what's really good there. What's really good are these things in the middle, right? So nuclear power is, I'll give you one simple analogy. The nuclear aboard my submarine was an 80 megawatt nuclear reactor, which is enough electricity to probably power a small town or village that you may live in. And that amount of uranium that it took to operate that reactor would fit in a 55-gallon drum, and it would last for 15 years. Actually, in a civilian environment, it would last for 30 years. So even though nuclear is very expensive, the marginal cost for the fuel is so low because it lasts a long time. Hydro, offshore wind, onshore wind, and solar, these have the best marginal cost of fuel, which it's because they approach zero. Today, we don't have to pay per gust of wind or per photon. There's some cost associated with moving water around, but that's actually captured in a different bucket, the ops and maintenance bucket, which is over here to the right. So let's go ahead and move over there. Ops and maintenance. Well, let me just stop for one moment. Those with the higher marginal fuel costs, there's none that are completely red, but if you look at the coal, natural gas, fuel cell, that's because they're running, in the case of, each of those things, they're running natural gas or hydrogen right now as their source. So you do have a marginal fuel cost associated with those. Let's continue with our marginal cost bucket. And in this, let's look at how hard is to maintain something. So this is, what does it keep, what does it take to operate that plant? Is it complicated? Is it easy? All those things at the bottom are pretty simple. They require next to no operators. Or hydro, maybe just one operator. Offshore, onshore, solar, and fuel cells, very little moving parts. I mean, winds obviously has some moving parts, but solar and fuel cells, almost no moving parts. You can monitor those things remotely. So they're, very, very inexpensive operations and maintenance. Nuclear requires highly qualified people and expensive parts to go fix. Coal, it's, think about lugging that coal around and getting it from the mine onto a train, onto there. It's a lot of work associated with that. Natural gas has pipelines, so it's somewhere in the middle. So that M bucket is the marginal cost. So if C is how much your car costs per passenger, M is, what does it take to put gas in the car and maintain it? And then you look at how much energy is produced per unit. So the bigger something is, the more it helps you really keep the cost down. So that's, as you break apart each thing, you have to kind of understand how each of these play, because what you'll find is to achieve an optimal cost resilience and sustainability, there's probably no single good answer. Instead, the answer is going to be bringing these different sources together. Of course, what brings these sources together from way back in slide 3 or 4? It's a microgrid controller able of bringing these things together. All right, we talked about cost. Let's talk about reliability and resilience. I do want to draw out one point here, is that reliability and resilience are two different things. And it's a bit of a fine point, but it's something that I find that people use them without necessarily meaning an exact definition, and they do mean different things. So what is reliability? It's the ability of a power system to deliver electricity in quantity with the quality demanded by users. Highly reliable systems have a very low frequency of interruption. These things operate all the time and they hardly ever break down. Now let's talk about resilience. Resilience is the ability to reduce the magnitude and duration of disruptive events. The effectiveness of a resilient infrastructure depends upon its ability to anticipate, absorb, adapt to, and/or rapidly recover from potentially disruptive events. So the story of a resilient infrastructure is not necessarily that it's reliable, but it can respond quickly. And a reliable system is not necessarily resilient. If you've got a large monolithic piece of energy infrastructure like a nuclear reactor, it's very reliable. It's online almost all the time. But if you have a problem and it goes down, it will not come back easily. Generally not, right? Conversely, you could have something, a power grid that is always exposed to severe weather and hurricanes and other things. It might experience outages, but it can recover quickly. Once again, you need a mix of both of these two things in order to deliver the kind of energy system that is going to meet the needs of everyone. And so once again, what are the two things that bring that together? A microgrid, bringing together different sources of energy that have different reliability and resilience. This is an example of how you might think about those concepts. So a highly reliable system, let's imagine that an outage occurs and a less resilient system, when disaster strikes, will go down, there'll be a problem, and it will require a long time, T3, T4 to recover. And even after, at the end of this time horizon, the system isn't back as good as it was before, but not a resilient system. A resilient system doesn't drop down as far because it's designed to anticipate and absorb that event, and it recovers much quicker. So thinking about those two outcomes and how do you want to solve for bringing them both together in the micro is one of the key things we think about. there is a growing case for that resilient infrastructure. So this is a graph from the National Oceanic Society, and it details billion-dollar disaster events in the U.S. And I'm not a statistician, but I'm saying there's more billion-dollar events based upon this graph than in the past. So we're living in a world in which the implications of a power outage are greater than before. And it kind of makes sense because in a world 20 years ago or 30 years ago, a power outage occurs. Well, we wouldn't have been having this class across Zoom. We would have been in a room together, right? The power could go out. Once again, we'd go out and watch the sunset and finish our lecture, right? But now there's ramification if the power goes down, right? We can't work. Kids can't go to school now. There's a lot of remote and distance learning going on. More and more healthcare occurs in the home now. Home dialysis. Many of you may have, in COVID as I did, begin to use remote medical assistance with apps and things like that. So we have taken, in places that in the past we put in resilient infrastructure into schools, we put resilient infrastructure into hospitals, but now learning and work and healthcare and are taking place outside of those resilient zones. So we've got to figure out how to go attack that. Resilience is important. So let's look at a microgrid in action. And we're going to end there because we've got 9 minutes, and then we're going to go to some Q&A, and I've got a few slides. So this is an illustration of a microgrid controller. This specific one is a piece of software that's developed by Schneider Electric, the company that I used to work there. I don't work there anymore, but they do make great products, and this is one of them. And what we're illustrating here is as follows. So you are looking at that integrated energy system. And we talked about that integrated energy system has things that make electricity. Those are the things in green. You can see that there are two, you see that little, there's X2 there. There's two different solar arrays at this site. There is a genset. In this case, this is a propane microturbine for this site. So it has energy generation devices, and then it has some loads. It has a electric vehicle. This is a smart load because I can tell that controller to stop charging a car on command. It has an HVAC system, heating, ventilation, air conditioning. This happened to also be a smart system. In industrial and commercial environments, most HVAC systems are digitalized, and therefore you can say, hey, heat up, cool down, turn off, etc. In this case, we can do that. And then we've got other loads, and these would just be those simple loads that, they're on. You turn, there's lights in the room. It's just dumb devices, the, laptop somebody left plugged into the wall, etc. The job of the microgrid controller is to create situational awareness of each of these things and then orchestrate it for the best outcomes. So let's look at a few things over here on the right. So one thing that I want to point out is this idea called a demand charge limit. So for commercial and industrial customers, generally a penalty is paid based upon the highest amount of electricity that's used from the grid. The reason that is as follows. If you have what's called a peaky load, like every now and again, I'm charging my car and have my pool pump on and doing the laundry at the same time, I'm going to use a lot of electricity, right? And the utility has to put a transformer and a gear and switch gear in that panel in your house has to be big enough to serve that peak load, even if the rest of the time your load's very small. So the utility has to have some way to recoup that max load infrastructure. That's what that demand charge limit's about. The reason that we monitor that here is that in this case, if you go above 800, you set a new demand peak. And setting a new demand peak means that you pay even a bigger penalty. So this microgrid is going to try to, no matter what happens, not exceed that peak. Here we're looking at grid consumption. What that is right now, the utility grid is providing 56% of the energy that's required. Where's the rest coming from? Well, it's coming from some solar, some batteries, et cetera, that's going on right now. In this case, there's been no off-grid instances for this microgrid. It's tracking how many things happen. The next thing here is very important. Weather is one of the single largest correlated variables to energy. Why is that? Well, weather is correlated to load. The hotter it is, the more your air conditioning load is going to be. And the colder, if you have electric heating, the more load you're going to have it that way. Weather is also highly correlated to energy production. The sunnier it is, the more solar panels are going to put out. However, the hotter it is, the less efficient solar panels get. So a cool, sunny day actually results in more electricity production from solar than a hot, sunny day. So knowing what electricity is going to be important because this weather also is like cloud cover. So if we're looking at this grid, we're looking at, okay, what's the temperature now? What's it going to be? What's my cloud cover? That's going to give me insight into how well my solar is going to operate. Is it going to rain? Okay, that'll impact my solar as well. This pressure and MBAR, the reason that's important is that it helps us understand if severe weather is likely. Is this microgrid likely to be exposed to a power grid event where bad power quality could happen, or the grid could be lost? Then I'm looking at things like wind speed as well. Maybe I have wind, or in this case, wind speed actually can cool down those solar panels, so it can be helpful. And finally, based upon some calculations, what's the probability of a storm? If the storm probability is high, I might go into a different kind of mode, which I'll talk about here in a second. All right, so let's see how this microgrid works. So energy cost management. So I'm going to alert you to a few things. First, on the very top, those different colored bars, dark blue, light blue, dark blue, orange, dark blue. Those represent times of different electricity cost. In this case, on peak was somewhere in the neighborhood of 15 cents per kilowatt hour. That's what the customer is going to pay. Off peak is somewhere in the neighborhood of 5 cents a kilowatt hour, and mid peak is roughly 10. So why are those things where they're at? Well, let's think about this. 4 o'clock to 7 o'clock. What's going on then? Well, people are getting home from work. They're starting up their stoves. They're turning on their television. The electric grid is starting to be loaded up. And that exact time, the sun is at such an angle that solar arrays are beginning to put a little less out. So you've got kind of a double whammy going on, high loads, and your renewable energy is starting to die off. The utility is going to charge you more during that time period. Why off peak in the middle of the night? Well, that's 3 a.m. to 7 a.m. No, not very many people at work. The utility has a bunch of extra capacity. Maybe the wind's blowing like crazy on their system. Using these time of rates, this is a regulatory mechanism that attempts to create some elasticity in consumption. It attempts to say, hey, if you use it when I want you to use it, you'll pay less for it. So that's the first thing. Now, when you look at these lines, let's start at the bottom. The yellow line is solar energy. And you can see that, sun rises a little bit. Right around 10 a.m., solar really starts to pick up, reaches its peak around 1, peak stays till roughly 4, and then starts to die off, just like we said, right? So that's solar energy. That's solar energy on the microgrid. Green is the battery. Now, I'll come back to a moment and tell you why the battery is doing what it's doing. Let's go to the top. The top, there are 2 lines. There's a blue line and a black line. From midnight till roughly, 8 a.m., the blue line and the black line are equal. And that simply means the blue line is the energy that you're drawing from the grid, and the black line is your total consumption. Why is the blue line less than the black line? Well, you're making some of your own energy during that time period. So that area between the blue line and the black line is actually the energy that's being made by your own solar system. Now, let's talk about how this microgrid works in order to save this customer money. You can imagine that if possible, we would say, hey, why don't you use less energy in the middle of the night, more energy in the middle of the night, and use less energy on peak? Well, maybe using more energy in the middle of the night isn't really an option because your people aren't there unless you have a battery. So that's exactly what happens here. You can notice that in the middle of the night, that green line going negative, that means that battery is being charged, okay? That battery is being charged up. Now, you'll notice that right around 8 a.m., that battery, or the battery is discharging. Why would that battery be discharging? Because it's not the on-peak time, it's just mid-peak. Why would I use some of that why would I, waste some of that battery? Remember that demand peak we talked about? 800 kW? The system forecasted that that site was going to use more than that demand peak. So it dispatched the battery to shave that peak and avoided that fine. Now then the controller had a decision to make. It has to say, okay, great, we're not at that peak period anymore, but now do I have enough capacity to shave, to use as little energy as possible during that on-peak time? It did a calculation that says, you know what? It's not supposed to rain. It's not supposed to be cloudy. That solar energy should be here. Let's go and charge this battery as much as I can while that solar's out. This customer also might have said, you know what? I want as green energy as possible. So using that solar energy to charge the battery and then dispatching that later in the day actually improve their overall carbon footprint. So now let's look at what happens at 4 p.m., that time of high peak. What does the battery do? It dispatches. It creates that nice gap there between how much they're using and what they're buying from the grid. This system in this fashion, by shifting energy consumption and by shaving peaks, is creating energy savings to the customer. And this is that peak demand management I was pointing out right there, just so you can see what happened when the battery dispatched and caused that peak. Now, by the way, you don't always need a battery to do peak management. Some of you may have a Nest thermostat. It's designed to do something similar. Taking load off of the grid has the same impact of putting generation on the grid. So if you have a microgrid, you can turn off some load for a while. It has the same impact of making it. So, and here's an example of this. This is a story of what's called demand response. This is an economic program that some people are eligible for, in which they can leverage their ability to create flexibility of demand to say, hey, if you tell me to, I'll use less right now. I'll stop doing my laundry. I'll unplug my car. I'll turn off my pool pump, whatever. I'll turn lights off in the house. The utility in this case sends a signal and says, I want you to have the lowest possible energy consumption possible during this windows. You can tell when the windows are because the microgrid controller shoved the energy down as low as possible. Now you'll notice in this case, the microgrid is using heat management to do it. So the utility is incentivizing reduced consumption during a window. And the way this building did it was it preheated the building. So in this case, this is a facility in France, by the way, and so everything's in Celsius. But you can see the dashed yellow line is temperature in the building. You can see that we preheated the building right here, and then we turned off the HVAC, which then caused the temperature to coast down, but it was still in that comfort range. So this is something where you're co-optimizing your systems, in this case, an HVAC system, that essentially makes HVAC a battery. It turns your house into a thermal battery by controlling the temperature in your house. So very similar to the battery, but using in this case HVAC. You can do the same thing with EV chargers. You can do the same thing with any other controllable load. Finally, storm management. So there might be times, remember that storm predictability, when there is a high likelihood the next 2 hours of severe weather. Maybe I'm in an elder care facility and I have people on dialysis. I have, critical healthcare things going on. I might choose to configure my microgrid for resilience instead of cost savings based upon that. And so by integration of a weather service with a microgrid controller, you might do things like, you know what, I'm not going to shave that peak. I'm going to charge the battery all the way up. I'm going to go ahead and get that generator ready to go if I need it. I might even proactively separate it from the grid because I think there's going to be a whole bunch of lightning and other things. I might get rid of non-essential loads, and I might isolate my sensitive equipment. A microgrid is capable of doing all those things as well, helping you solve for that storm scenario, and assuming that's a metric that you want to solve for. Final slide, I want to kind of share where we're at. Many of you, I'm sure, have read Jeffrey Moore, Crossing the Chasm, one of my favorite books. And it was written in the 90s, but it's still amazing today. And it kind of talks about how you bring kind of revolutionary change to market. He was really talking about the .com stuff, and it applies to energy in this right now, though. And that it's very difficult to get to. Remember those slow build up of those curves? Why did it take 60 years from oil fine to oil and energy? Because it takes technology, regulation, and business models to all align. In terms of microgrid, we are still pretty early. That chasm represents the difficulty of getting to the main market, of aligning these three things, of creating companies or organizations with a singular focus to go do it. I think we're getting closer to jumping over into the early majority now, but those, because people have been working really hard on knocking down those technical, regulatory, and financial hurdles, but they absolutely exist. So what are the solutions that allow you to do some of that? One big one is cloud connectivity. When I first started doing microgrids 20 years ago, I would have had to have like 4 computers in your house. I could do a microgrid. I'd have one talking to the utility retail price markets. I'd have one connected to, your smart thermostat, or it wasn't smart at the time, but directly to devices on your furnace. And I'd have all this, I'd have to write programs, extremely expensive, bespoke. We can move that stuff to the cloud now. You can have most of that analysis, most of that decision-making done in the cloud, where it's spreading the costs over many more people. You're tapping into AI and getting better outcomes than ever before. You've got people that are, can do sophisticated analysis on it, and you don't have costly on-site infrastructure. So cloud connectivity is a huge way to start to get over the chasm. The second thing is this idea of kind of systems that are pre-built in the factory environment. In the home, for example, once again, I could put a microgrid 5-10 years ago. Some of you may have done that, but you had your panel that then you had to wire to some solar inverter, that then you had to wire in some lead acid battery, and you had to, put all these different components that weren't designed to work together, figure it out. When one thing broke and took the whole thing down. You can now buy devices that have the solar inverter, the electric panel, facilitation for smart load, smart batteries in one device. And that device is tested in the factory. Everything's designed to work together, and it's automatically cloud connected. And finally, the final thing is business models that transfer risk from energy consumers to specialists. One thing that you may have already seen in this is the story of like a PPA, where I don't have to have, $25,000 of cash laying around to go put solar in. Someone else is willing to go and buy those things and vet all those vendors and make sure it works. And I simply have to pay a price per kilowatt hour. That's an example of a simple business model that transferred some risk away from the consumer and into the specialist. These are the kind of things it's going to take to allow microgrids to proliferate really across residential, commercial, and industrial loads. And that's my final slide. I add one more note there. Energy policy aligns with societal goals. Also very important. So with that, we can go to Q&A.
Thank you, Mark. Thank you so much for that very informative tour through microgrids and the energy space and how it interfaces with digital distributed energy systems. It was very helpful. Joe and I will handle the Q&A. Joe, do you want to start with what's in the chat?
Well, there's one comment initially, and I believe it pertained to the slide that showed the cost of electricity in the United States. And it's a comment that simply says that it seems like those retail prices are for the electric supply and do not include the delivery costs. So just a comment.
There we go. Yeah. That actually was the retail price, but the difference is that it was 3 years ago before natural gas went up so much. So that was, and the other thing to remember is that was a blend of residential, commercial, industrial. Industrial rates can be half of what residential rates are. But it is important that you always look at your bill, because you'll find that there are many different aspects to it, right? You may have a volumetric aspect, a price per kilowatt hour. You may have some charges from a transmission distribution utility. You may have demand fees. You may have power factor fees. You may have special taxes and other things. So utility bill isn't as simple as maybe it used to be.
Indeed. Thank you.
So for me, reliability means, does it work the way I expect it to work? Solar PV is very highly reliable. No single generator is very reliable when it has many moving parts to it. Backup is only used to correct for reliability issues. Dependability means, does it provide the electricity when I need it? And he's saying all systems, let me finish this, all energy systems need to have energy storage with them in order to be dependable. The whole grid is dependable and reliable by the way it is designed, constructed, and operated. Because the grid has energy storage and backup. So that's a comment, I guess, rather than a question.
Yeah, I largely agree with it. I think just make sure your definition of energy storage, that you're not limiting yourself to, battery energy storage. There's a lot of ways to store energy in things, even mechanical systems and flywheels and even water behind a dam is energy storage. So just make sure that I agree with the definition, but as long as I find a lot of people, they go right for battery energy storage. And oftentimes that's one of the more expensive and least effective ways to get what you need, but not always. Sometimes you need it.
I guess it depends on the magnitude of the energy you want to store, right?
It does. It's magnitude and also how fast you need, at what rate you need it back. So it's also form factor issues. Are you considering the circularity of it? I mean, there's a lot of dimensions, and there's a lot of forms of energy storage. Energy storage, I think, needs its own session of its own. It's a big topic.
Yes.
So one.
Go ahead.
Go ahead. Sorry, Chuck. So one comment before I ask your question, and that comment is that the very well-informed, practical, and experienced presenter. Thank you.
Thank you.
And the question is, where do you see microgrids being developed? Within the states, residential markets, commercial, industrial, and who are the early adopters?
Yeah, so some of the earliest adopters were those that, they bought it for resilience. And then you begin to layer on sustainability goals. So imagine, a college campus, a military base. You needed the backup power anyways, but then you begin to have goals around resilience. Around sustainability, and you could benefit from some of the fact that solar and wind have no marginal energy cost. And so they were some of the first movers. I've done lots and lots of municipal campus microgrids, military microgrids. Industrials tend to be a little harder, and there's some reasons why. So energy assets don't pay themselves back real quickly. So if you look at any regulated utility and you look at their rate of return, their rate of return is generally 8 to 12%. That doesn't equal, so in other words, they're buying energy infrastructure and that's the kind of return they're getting. That doesn't equate to a 3-year ROI. When you go to a manufacturing facility, they're like, you know what? I don't know if I'm gonna have this plant here in 5 years. I'm not going to put in some microgrid that's going to take 12 years to pay off. I just don't know. I don't want to build it for the next guy. So, industrials have been a little bit harder from that perspective because energy happens to, once again, it works by the laws of physics. And as long as you're working with reputable vendors, it's very likely to deliver exactly the ROI that physics say it should do. But it's not likely to do it in 3 years, like you may have heard some of your companies talking about. So industrial is always a little bit slower. When I've done industrial stuff, it's been at, let's go to Ford's corporate headquarters or R&D center. Well, of course, they're going to do it there. They plan on being in Dearborn for another 50 years, so no problem. Commercial has another problem, and that's called the split incentive problem. And that if you're an owner-occupied facility, yeah, you might be able to make it work, right? That makes sense. I own it. I own the building. I stay here. It's whatever. But a lot of buildings aren't that way, right? You've got a building owner, a building tenant, and a building manager. And the tenant might only have a 10-year lease. There might be a 3-year contract every year to put a new operator in. And so you end up with this problem where you can't align time horizons because of that split incentive. And who benefits? So you put a microgrid in and somebody pays lower energy costs today. Well, who paid for it? Did the building owner pay? How do you get benefit from that? So in the commercial environment, you've got to go to those places where generally owner occupied is very helpful in that kind of environment. But I will tell you that microgrids are proliferating across all segments despite those challenges. And it has to do with, they're becoming they're becoming less expensive, and the incentives for using distributed energy resources, solar, wind, fuel cells, et cetera, are quite advantaged, right? There's significant incentives as function of the Inflation Reduction Act, and there has been for some time around each of these things.
It's going to cost an awful lot of money to build more transmission capability over long distances compared to building distributed energy systems locally.
That's a great point, and it brings up other challenges. Look, we talked about what it took for oil and gas to take off, and that was pipelines to really make a difference. And it's going to take pipelines and electricity for solar and wind to have a profound impact. But it's challenging. You get the same challenge you have with pipelines. I mean, I grew up in Ohio, and a lot of my families, grew up in farming with a lot of farmlands, and whose farms are going to get cut across by this transmission line? No benefit to the local community, no benefit to the state. And now you can argue, there's great arguments, by the way, that people will make, but they're kind of wonky engineering arguments like, well, your rate base, everything's, you're going to have lower energy because the ISO prices are going to be less, but that doesn't always make sense to the conversation down at the corner gas store where some of this stuff happens. So it's tricky.
But if we price carbon, the whole world changes.
That's a great point, Chuck. Yeah, you start, that's where you get regulatory mechanisms aligned correctly. And then, you got to have the technology and the business model still, but that's key.
Yeah. Joe, do you want to get this next one about cooperativity, solar energy community cooperatives?
Yeah, but before I tell you what, Chuck, before we touch on that one, since we talked about a regulatory, let's just touch on this one. What are most important impediments to adoption? Cost, regulatory, connections, technology. You started to talk about some of those things in your last conversation.
Yeah, they all have to travel together. So I wouldn't say that any one is more important. I think what the laggard does, a lot of times is regulatory, and into that you've got to throw permitting. An interconnect agreement in most states right now is 3 years for a large, for a commercial industrial microgrid.
Wow.
So you better be a patient person if you're going to put one in right now.
Wow.
Okay. And as Chuck had mentioned, thank you for that. And as Chuck had mentioned, we received an email this morning on our website, Maria website. I'm not sure exactly where this fits into the conversation, but the individual asked that if you would please touch on the topics of solar energy community cooperatives. And they listed 4 situations or examples. The first one being an example in the Northeast US, range of size, number of cooperative subscribers, a few good examples.
Yeah, I'll tell you some of the challenges. And I'll broaden it beyond cooperatives. So because cooperatives, there's actually a root problem that led to cooperatives, but still hasn't solved the problem. And when I say root problem, it's not exact. It's a situation. You could call it a problem or not, depending on your perspective. And that is that, there was massive infrastructure invested in order to get that power wire to your house. Infrastructure invested by public utilities, by municipalities and cooperatives that go well beyond what any person's going to pay for their power in probably their lifetime. Let's say decades and decades and decades. And to reflect that, the policy in the U.S. And many places around the world is that for transmission and distribution, so that's the big wire stuff, not the stuff in your home, a company has a monopoly on delivering those services to you. And there's a bunch of cool writing on this, and it goes back to the early 1900s. And there's a cool movie called The Current War that if you haven't seen it, everyone on this call should go see The Current War. It's actually a real movie with big actors in it. And it was a story of Tesla, Westinghouse, and Edison and how we got the grid we got. But people were building competitive utilities, just like they were building competitive railroad, literally transmission lines right next to transmission lines. Stockholders were everybody was getting, in trouble. And the states finally had to step in and say, this is the Wild West. We're not going to do it. We're going to give one person the exclusive license to sell power to a consumer. And over time, that was broken down. So at first, one person would do the generation, transmission, distribution, and sale of electricity. That's called a vertically integrated utility, and it still exists in parts of the U.S. today. North Carolina, South Carolina, Georgia, Mississippi, those are all non-competitive environments. One company, could be Southern Company, could be Duke, deliver all those things. But in most of the U.S., that's been split apart. But one part remains regulated. That's transmission distribution. That's why even if you buy your electricity from an energy retailer, you might see, oh, and here's the charge to Exelon, the wires charge, they might call it to Exelon. They have the exclusive right to sell electricity across a legal property line. So you could take a generator on your property and power your barn, and Exelon doesn't even know about it. They don't get a cut of it. It is illegal for you to send that power across the property line to your neighbor in nearly every jurisdiction in the U.S. and in a lot of places of the world. It's illegal. So the challenge that created, especially when you start thinking about, solar energy, things like that, is this is energy that a lot of people covet, but not everyone can afford. Not everyone has the credit or the capital necessary to go spend the kind of money to go put this stuff in. But it was illegal. If, let's imagine, I could buy one, it'd be illegal to give it to my neighbor who also wants clean, green energy. I'm not allowed to do it. So, so far, public utility commissions have not been willing to think about breaking that protection around T&D. And there's still some good reasons why. It's a really complicated topic that goes beyond this call, but there are some good reasons why they don't want to completely break it. There's a lot of people's pension funds that have utilities in them, things like this, and there's a lot of other externalities. But they started to think, what's some compromises? So, some places like California and other places led the way a little bit. Say, okay, I got an idea. Let's not go and, I won't sell it to my neighbor, but can a few of us go in together and kind of put our own solar array in, and we'll still run it through the regulated utilities line. We'll still pay Exelon their cut, but I get my renewable energy. That is what most of these cooperatives have kind of turned out to be. And they do provide you some ability to prescribe the energy you're going to buy without waiting for a utility to go do it. However, most of them, and there are some exceptions, most of them are not microgrids in any way. If the grid goes down, you're not getting energy from where it was made to you. Sorry, you're out of luck. There are some, though, there are some newer concepts. You might hear them called perfect power parks, things like this, where people co-locate a bunch of industrial around a resilient energy infrastructure. And they have some of the same setup. You're still not cutting out the T&D company. They're finding some way to kind of take their cut on that, but you are getting some of these things. So yes, There is legal problems, who's allowed to do what and where, regulatory issues. Most of the times they don't help you when there's outages unless you want these really special examples. So all those things you mentioned are all part and parcel to this challenging environment we live in.
Thank you. Thank you. Thank you, Mark, for your detailed and interesting answer. A lot of things I was not aware of. The next question is free software for doing simple assessment for microgrid applications with sensitivity analysis. Does anything exist that I could use?
Yeah, there's something called Homer that was created by the DOE. It was originally created, I think, for combined heat and power, but it was expanded. So now it's like publicware. And I haven't downloaded it in forever, but I'm pretty sure it's still out there because it was created by the US DOE. Now, many companies have taken the Homer code and forked their own code off of it that have added much more. I mean, look, Homer was kind of a little bit written for engineers and scientists, so it's not maybe the easiest thing, but many companies then have taken and built their own special UIs around it, made it a lot easier and enhanced it and stuff. And those likely aren't free, but I haven't looked, so.
Yeah,
Do you have any? Sure, you have any examples of current microgrids serving normal communities?
Yeah, sure. I mean, well, I guess we'll talk about normal communities, but I mean, in Montgomery County, Maryland, you may have, I've been involved with several microgrids there. The Montgomery Public Safety Headquarters is a solar plus combined heat and power microgrid that services critical facilities for the county, provides EV charging for community vehicles, actually anyone that wants to go there, and creates a little bit of an oasis if power goes down where they can provide some basic services to folks that might not have shelter to go to, et cetera. The same, there's 2 busing depots now. One's complete, one's just announced from Montgomery County, where electric busing depots, a microgrid, doing some of the same things, charging EVs, charging electric buses, but also providing, a place where folks could go charge their phone if they, if the power's down and maybe they're not living somewhere where they can have access to power. Maybe you can go plug in a, medical monitoring device, et cetera. So there's a lot of examples of community microgrids like that. They're generally centric upon public infrastructure. The microgrids that might serve like a subdivision, there has been some announcements on that. They generally, though, because of that regulatory challenge, they have to be owned by the utility. And it is a real sticky situation because when a regulated utility does something like that, they have to justify why they're spending money there instead of spending money somewhere else. So, it's when they sit before the rate commission and someone says, well, why didn't my street get that? Why did you only do the rich people in this part of town? The people that are rich enough to own Teslas, now you're going to give them more things. You get these kind of arguments. So it is difficult to do residential cluster microgrids under the current setups.
Wow. It's all the stakeholders have to be involved.
Yep. Doesn't keep you from doing your own home microgrid. Of course, you can do that behind the meter.
Right. Gordon has another comment. I haven't really been able to understand the value of microgrids. All the characteristics that you mentioned about microgrids also exist with our general central grids. And all the issues with central grids also exist with microgrids. So why is microgrid such a buzzword?
It's a buzzword for a lot of reasons. One is that with a central grid, you get the average that most people of energy that most people want around you. Let's go back to that hospital and elementary school situation. The hospital did not get what it wanted. It got the grid that sometimes goes down. The school was probably paying too much for electricity because they're paying for more resilience than they need. So you can get a more tailored outcome in a microgrid that's better aligned. You can get better value for your energy. The second thing we didn't talk about is the co-location of energy supply and demand. When you put the supply right next to the demand, you eliminate all the variables that can cause an outage, severe weather, drunks hitting poles, all these things that happen, right? Doesn't happen if it's sitting right there, in your own garage and you're creating it. So you've co-located supply and demand. You've eliminated grid losses as a result of that, and you've tailored the power to exactly what you want. Those are the advantages over the centralized bulk power grid. Bulk power grid's been great. It's electrified us to where we've gotten today. There's better outcomes possible. Microgrids are a mechanism to deliver that.
And there's also the entire world that doesn't have the grid, right?
That's right.
So building mini grids, yeah, okay, call them grids for that village or grids for that establishment of industrial capability in a greenfield, but it's a whole lot cheaper than trying to run transmission lines from a centralized power plant. Right?
Absolutely.
Okay. Ron's saying, I don't think Homer is free. He put a question mark.
Oh, well, sorry.
We'll have to look into that.
It used to be free.
Yeah. So are there any other questions? There's lots of comments here, Mark, about thank you, very good program, highly informative, et cetera, et cetera. We really appreciate your time. And I just want to ask one question related to your cost and all those green dots.
Yep.
On fossil fuel generated power. How in the world, if we put a tax on carbon or a cost on emissions and we have to capture the CO2, those costs then move into yellow or red territory?
Yeah, that's right, Chuck. That is what's going to happen because your marginal costs go up. So in Europe, there is something called the ETS, which is essentially a carbon tax on fossil fuels, and it has that exact ramification. Look, natural gas is still relatively easy to get. It is 40% greener than coal power. Chuck and I were talking before the call about, is it a bridge? Is it not a bridge? Natural gas will in our lifetimes continue to play some kind of role. So how do we think about, using those catalysts that I mentioned, mixing hydrogen with it, capturing the CO2, using storage. So we're not using so much peaker generations, inefficiency like that. That's how you can get more and more of that, solar, wind, maybe even nuclear onto the grid. And at the same time, provide better outcomes for people today. It's not a binary world. We're not going to wake up tomorrow and we don't have the transmission lines. We don't have the systems to have massive penetration rates. We've got to navigate a chart through this.
Yep, we sure do. There's lots of work to do. Thank you, Mark. Thank you so much. Does anybody else have a question before we tell Mark to have a good evening? Or you can stay on, Mark, if there's going to be a connections period. If they have other questions, we can open up the mic. And if you want to stay, you're welcome to, but you don't have to feel obligated to stay.
All right. Well, please feel free to email me. I actually have got to get on another call. So.
Oh my goodness, Mark. Okay. All right. Well, thank you for your time.
Thank you, guys.
Thank you.
Pleasure spending time with you tonight. Take care.
Yeah.
Bye-bye.
Bye.
Anybody have any other questions, comments, thoughts? Anybody here? You want to unmute?
Yeah, it was a really great across the board compilation of everything about how our electric system works. The challenge is, how do we fix it?
I have a quick question.
Sure, Dave. Go ahead.
So it was an amazing presentation, extremely informative. I really appreciate it. And thanks you guys for helping put that together. I have solar now that's generally as much as I would use for my charging my EV and my house and everything, but I'm still connected to the grid and I have no storage. So if I was to do this microgrid, concept at my house, do I have alternatives to firing up a gas generator or a battery? I mean, they're the only two things I would think of that would supplement my electrical, my solar panels. Am I missing something?
No, not really. I mean, there's fuel cells and things that are, a little bit on the market, but there are not a lot of alternatives
Well, there's
locally
also
that you could.
combined heat and power. There's a combined heat and power system as well.
Well, most of those things when you're looking at combined heat and power for a home situation, that becomes a heat, it makes sense for heat where you have a heat source and or a heat demand, which a house does have, but now you've got a little bit more work to do to fill in with fossil fuels in order to make that whole system work. But
right. Well, and I have, I can fire with wood, I can fire with oil, but I still need electric to blow those around and stuff. And I was just wondering if there's any commercially viable alternatives to a gas generator or a battery. I wasn't aware of any.
yeah, well, I think as Chuck mentioned, that the combined heat and power kind of organizes that. But and you have, in a way, your wood heat is a primitive form of a microgrid, because you have an alternative energy source that you could work with.
Right.
So
But you're the microgrid. You're putting the wood in the fire.
that's right.
Yeah, but I still need electricity, and when my if I'm saying I'm not going to tie to the grid, or I'm not going to depend on something else other than the grid, it gets pretty expensive, and there's not too many alternatives that I'm aware of.
Right. Yeah. That's right. One of the things that's been in the background that's an interesting, the fuel cell is in a way something they have small scale versions of them. The famous one was the Bloom box came out a few years back, and there's been some alternative suppliers who've been offering those as an alternative electricity generator, which basically uses natural gas as a fuel. So that's a way to do that if you're supplied with natural gas. So sometimes people use different forms of backup for their solar. So that's one thing you could explore. It's not super cheap, but it's not outlandish either, I think.
And you're saying a fuel cell, where you mean I would generate hydrogen during peak sun and then burn the hydrogen, or?
Well, most of the ones that are commercially available, you're using natural gas as a source. So they're basically generating electricity from natural gas.
Okay, yeah.
Again, I'm not sure what is available commercially for residential
Right.
homes.
Yeah,
You'd have to have a source of hydrogen if you did not want to burn natural gas.
yes, that's the important thing. It's what is your fuel source? It's not going to be as green, but it's your alternative to the solar. You have to factor in, how can I get it, and is it affordable, and what kind of infrastructure do I have to have in place in order to support it?
Yeah, I didn't know how close we were to something small that was generating hydrogen that I could turn around and use a little
Not close
generator.
enough.
Yeah, there've been some experimental. There's a guy in New Jersey that's been running on hydrogen for years, but those are not commercially available things.
Right.
Well, although there's a huge push for developing new technologies that are electrolyzers at the kilowatt scale level for industrial and residential applications. So there's an awful lot being done in electrolyzers to bring them into the retail market at some point. And I don't know whether it's 2 years or 5 years away, but it will happen.
Yeah.
Yeah, and that's kind of happening on the car scale, just like we're finding with using the vehicle to grid kind of thing. There's also fuel cells that have been developed for cars, which are home scale basically, that are again not here readily available that you can look up in a catalog and buy, but they're out there, and getting experience and moving along. So hopefully not too far out.
I'm counting on you guys to let me know when that's ready.
Yeah.
We'll try.
I really enjoy your programs. Thanks again.
You're welcome, Dave.
Does anybody else have any questions or comments or thoughts about the presentation this evening or
Or
Yeah,
other
other
topics
topics.
you guys want to hear about?
yeah?
If not, we'll say good night.